Good morning, all. I was just looking at the syllabus and realizing, wow, we have 3 weeks left. Can't believe it. Where does the time go? So, today we are, and tomorrow, we're doing 4.5, which is optimization, is the usual title that calculus books give this, but it has to do with really just the one of the main reasons calculus was invented. In other words, to kind of maximize things and minimize things. And we saw earlier in this section that maximums happen on a curve, up at the top of it where the slope is equal to 0. And so at the start, we just said, hey, here's this cubed graph and go find the maximums and minimums. But sometimes those maximums can be actually somewhat practical. And I say somewhat because, well, I'll show you what I mean. So I want to start off with kind of a classic question. We're going to spend today and tomorrow on this topic because I'd like to give you enough time to kind of soak on this so that you can actually apply it to something in life. And I'll just kind of talk about that as we go. But let me just get right into it. So 4.5 optimization. We're going to start off with kind of the most classic calculus problem. So how to optimize something. And so let's optimize this. If I had kind of a rectangular piece of cardboard, let's say, or paper, whatever. Say it looked like this, and let's make the dimensions of it, I don't know, 32 centimeters by, let's see, that looks a little more than half, so let's make that 18 centimeters. So I got this rectangular piece of paper, and you're gonna make a box out of that, and this is the easiest way to do it. And by this way, it's kind of a sheet metal example. So you come in and you make this cut in the corner and chop that little chunk out of the box, and you do the exact same thing in every corner. And you might notice that this cut you make in it, every one of these, I'll say C for cut, I guess, every one of these cuts has to be a square and of exactly the same size for this to work. So if I chop that out, what do I have left behind? Well, I have something that looks like this. This is just one way to do it. We'll just kind of sketch it. You'd have something that looks like that. And of course, if you took the leftover kind of a plus sign shape that you have and you folded the sides up along those lines, then you'd have this little box. Maybe it's that tall. I used to teach drafting, so I'm pretty decent at drawing three-dimensional shapes quickly. But that's the idea. So in a real context, the cool thing is that the bottom edges of that box would all be folds, which means they're not going to leak or let stuff out. And the sides would have to be kind of welded together, taped together. In the case of a piece of paper or something like that, you'd have to weld them at the corners. And so, great. I mean, that's kind of a cool way to make a box out of a piece of paper. And again, I wish we had time, because one of the things I think that makes this kind of thing fun is to just actually do it. I mean, even though you're cutting stuff and playing with pouring rice into it or something like that, it's kind of fun just to see it actually happen instead of just talk about it and do the math. So feel free. So what we're trying to do really is, well, optimize this. I mean, if you have a 32 centimeter by 18 centimeter piece of paper or whatever it is, cardboard, sheet metal, optimize means I'd like to get the most, I'm going to use this box to hold rice or whatever the heck. And so I'd like to get this thing as, well, the biggest volume I could possibly get. And so when I say optimize, I really mean, you know, how do we max the volume in this case out? Optimize the amount of material, like we're going to waste it. And so can you picture, just to visualize this, just to give you kind of a chance to soak on it, if C is small, if you make a really small cut in the corner, you might say that's a good idea. I'm going to make a tiny little cut in the corner, because if I do that, then I'm going to get a really big box. And you're exactly right. You will get a really big box if you do that. But of course, the downside of that is your box is really shallow. So, you know, is that a good volume? Is it better to like have a nice big wide box? And it won't be very tall, but will that give you the biggest cut? Or perhaps, no, maybe that's not the case. Maybe C is, I'm not going to say large, but larger. If C is larger, and of course the C here is, you know, that length. I mean, do you see that in the picture? Whatever length you cut C at, that's how tall the box is going to be, right? So if I make this a little bit larger, then of course that side length is going to be quite a bit taller, and that's great. Oh yeah, taller is better. But unfortunately, the result of it being taller is it's not going to be as wide as it would have been, and it's not going to be as long as it would have been.
Isn't the volume in this case, wouldn't it kind of be equivalent? Because you're not exactly, like, even though you're changing the dimensions, doesn't the inside, like the technicality of how much water or whatever you're pouring in it, stay the same?
Absolutely.
You're just changing the shape of it.
And that's what makes this kind of a fun problem, because it seems like, well, it's the same piece of paper. So, you know, however you kind of use it, it's the same piece of paper. Now, if you go get a different size, not 32 by 18, but another size, you'll get a totally different volume. And so you might conjecture, as Eve did, that this isn't changing at all, and that, you know, it just sort of doesn't make any difference what you do. Well, let's go play with that. And ultimately, we're going to, you know, to get this right, to get it quick, we can use calculus and so forth. But the hard part of this section, just like the hard part of related rates back in the end of chapter 3, is you got to write the equations for yourself. And you might stare at this and think, and you frankly should, I have no idea like how I would do this. But what I want to illustrate is just how important, and I've said this a few times because I'm trying to teach you how to think in this class more than just how to get calculus problems right, is how beneficial it is to kind of guess. And so you might think like Eve, if C was small and or large, it isn't really going to make any difference. And so let's just go play around with this. And so to start any problem, if in real world as well as in calculus, you can actually do a lot more than you think you could by just kind of playing around. In other words, does the volume depend on that cut? In a sense, Eve's conjecture is no, it doesn't, because it doesn't make a difference what size the cut is. I'll get the same volume because it's a piece of paper. So, well, let's actually try it then. So let's actually put some numbers to this. Like, what if C was small, say 2 centimeters? So you know that the volume of a box is, if I call this the height and this the width and this the length, you know the volume is length times width times height. You've probably seen that before. So since I chose C to be 2, what does that do to the length and the width? That's kind of the question. So again, I just want to give you a second to think about that. I'm just going to draw this out a little bit. I'm going to draw it in its pre-folded up condition here.
So the way I solved it, I got 2 answers. Does that sound correct?
Potentially, yes. And I will say, one of the things that's interesting about these questions is some of you are quicker and sharper than others. I'm trying to go really slow here just to illustrate the fact that everybody can do this, but you got to not be afraid of playing around a little bit. You can't just stare at this and immediately expect to know what to do. But some of you will be able to proceed to calculus faster here than others. So I'm just giving everybody a chance to kind of make sense of this. And so the idea is if you made a cut of say 2, so you're chopping 2 off of this. Does it make sense, since the whole distance is 32 all the way to the outside, that you just lost 2 and 2? So that means this distance is down to 28 now. And the same thing would be true over here. If this is 2 and this is 2, it used to be 18, but because you cut 2 and 2 away, you cut 4 away. Now this side is down to 14. So basically your box is 32 in this direction and 14 in this direction. And so you can say, oh, okay, I know what to do then. The volume is equal to 2 centimeters times 14 centimeters times 32 centimeters. So whatever that works out to be. 28 times 32.
It's 14 times 28. 2 times 14 times 20.
Thank you. Yeah, we got rid of that. It was 28. So come on, man. Operate your machinery. So I got 784 for that, 784 cubic centimeters. So that's at least, you know, an answer. Like, okay, I at least see that I can figure it out. Like I didn't have to be told all the dimensions. I just kind of picked the one cut is 2, and I was able to sort of figure out the other 2. And then I multiplied them all together because that's what volume is, and I got 784. And so, okay, well, same thing, but what if we went down to this larger one down here and did the same exact thing? Again, we're just going slow, trying to figure this out. So I make a much larger cut. I haven't figured out what size yet, but I make a larger cut down here. So let's make that cut this time, I don't know, 5. So I'm losing all of these 5 by 5 squares out of it. And also you might think, well, you're cutting more paper away, so you have less paper to make your box out of. Therefore, this is going to be a smaller volume. Like you're wasting your paper. You're throwing more paper away than you threw away last time. That'd be a reasonable conjecture too. But if this length was 5 and this length was 5 and it used to be 32, then you're taking 10 off of 32. So now this distance is only 22. And the same over here. If this is 5 and 5, you're taking 10 off of 14. Now this only was left at 4.
Wasn't our original length 18, not 14?
Yes, I think I've blown it again. Yeah, it was 18, wasn't it? So that's 8. It's a good thing even one of you is paying attention. I was looking up at the one right above it and saw the 14. Yeah, so it was 18. So we're taking 10 off of that. So now it's down to 8. So thank you. So our box is 8 this way and 22 this way, but it's 5 tall. It's a lot taller, but then it's not as big on the top and the bottom. And so, boy, it sure seems like my writing is lagging behind. This could be another one of those days where I have to shut everything off. So let's see, volume then this time is length times width times height. Because I'm multiplying, it really doesn't matter which is which. I'm just saying 5 times 8 times 22. So that's 40 times 22. And I get 880. That's interesting. I got 880 cubic centimeters, not the same as last time. And so it wasn't obvious, but it turns out it actually does make a difference. And my second effort was better than my first. And so it turns out like a low flat box, although it's nice and wide because it's so short, you don't get a whole lot of volume out of it. But if you make a little bit taller, then even though you're wasting paper, it's kind of interesting. If you threw more of your sheet metal went in the garbage can here, but you actually got a box that held a bigger volume. And so now it's kind of like, oh, it's on now. Like what's going on here? So maybe the bigger cut is the better. So really what should happen with most of these questions is if you guess twice, you might be able to say, oh, I think I see what's happening now, but let's even guess 1/3. Let's even guess kind of a third one this time. Maybe I'll go back, instead of calling this larger, I'll call it medium. Sort of a medium size cut. Now let's actually go back and make C kind of a larger cut. Like say 9. Why is 9 a bad idea?
Because you'll no longer have a width.
Yeah, you got no width left. Does that make sense? So we can't go quite that large. Let's try 7. So again, to kind of quickly draw this out, what would that look like? Well, now we're really large. Maybe this is like a super tall box. I think I wasn't very fair about how far away those were. Probably more like that. So now I'm going to have a nice tall box like this. Is it even getting better? Is this going to be even better? Is kind of the question we're wondering about here. So I'm chopping off 9 and I'm chopping off 9 every single corner.
You're only chopping off 7.
7. Thank you. 7. So I'm chopping off 7, 7. Since that used to be 18, there's only 4 left for this length right here. And since the other side used to be, I better slow down, 32, and I'm chopping off 7 and 7, which is 14. 14, 32, and 14, is that 18? So doesn't that box look like this? It's kind of nice and tall. Or maybe it looks something like that. So the height is 7, but then that only leaves 4 for the width. And then the length is 18. Is that right? 18 and 14. I get so many dumb mistakes. I'd like to not make any more. So this time the volume is equal to 7 times 4 times 18. And oddly, I even got a different answer. I got 504 this time. So look at our 3 guesses. So
If I'm thinking, okay, can I go ahead?
Please, yeah.
If I'm thinking about this correctly, which I hope I am, is this using what we used last week in graphing maximas and minimas, but using this in terms of applying it to, instead of like, I don't know, stock or something, to box shape?
Yeah.
So you can find where your maximas and minimas would be?
Correct. Basically, today is just kind of a geometric introduction to this, but you can see that in business, if you're trying to maximize profits or something, it's just that in this section, we have to write our own equations. Nobody's just giving us one and saying, hey, here's the sine of X graph, go find the maximums and minimums. You got to make it yourself. But what I'm arguing is, number one, you're now convinced that it does make a difference what cut, which I don't think was obvious. But secondly, you now think maybe you could write an equation. Very few people can just stare at these problems and skip all of this guessing and checking. There's 2 things guessing and checking does. It helps you, do I actually even understand the question here? Do I even understand what's going on? And by playing around with it, you now understand the question a little bit better. Second of all, you now have some reasonable answers. Like, first of all, or I should say, does it make sense the medium? Are you now convinced that the medium is better, but does that mean 5 is the right answer? Like it could be 4, could be 6, could be 4.127.
Could I share the equation that I got just from looking at it?
Yeah.
So we're looking for the volume of a box, right?
Right.
So for that, we need length, width, and height.
Yes.
Well, our length is 32. Minus 2c, not minus c. So I did that wrong. And then our width is 18 minus 2c, and then our height is c, right?
Yeah.
So then you just make a x to the third equation with that, and then you can distribute it out, and then take the derivative, and then solve for the 0, and that should give you a minimum and a maximum. I just realized I did mine wrong because I did minus c instead of minus 2c, so I'm gonna have to go back and correct that. But yeah.
So let me illustrate what Vail just came up with. And again, some people are going to be able to come up with this faster than others. Perhaps you only need one guess or one, oh, okay, I see what's happening now. And then you write the equation down immediately. If you're really sharp, maybe you need none. I was not the student that just wrote this down immediately. I wasn't the sharpest student in class. I had to work at this. I had to think about it. I had to reason about it. I found this challenging. But my point is nobody ever showed me this. Like the fact that you can reason your way to it. They would just say, here's how you write it down. But what have we been doing every time? I mean, haven't we been taking to get this 28 right back here? To get this 28, didn't we take 32 and take away 2? And this is what Vail said a second ago. Take 2 of these cuts away, so it's 32 minus 2 2s. Wasn't this one down here 32 minus 2 5s? So I think I see a pattern. This distance here was 32 minus 2 7s. And so if I just left my cut at C, then isn't my height, this is what Vail was basically saying, isn't my height equal just to C, and my length was equal to 32 minus 2 C's, and my width was equal to my original 18 minus 2 C's. Isn't that what I was doing every time? Now that I've done it 3 times, maybe it's not so hard for me to write that down. And then what did I do? I said, well, the volume is equal to all of those multiplied together. And so now I have an equation. I have an equation, well, that I can maximize. And what does it mean to find a maximum? It means take the derivative and set it equal to 0. That's how you find the peak of a graph. And maybe you notice right now what Vail mentioned a minute ago, which is this is actually a cubed equation. Maybe you don't see it right now, but you're multiplying C times C times C. This is going to be a cubed equation. So you're finding the top, the peak of a cubed equation someplace. And now we don't have to guess. That's what's kind of cool. And we can get it exactly right. That's another thing that's really cool. So let's see, I have to take the derivative of this. And I might say here, just because it's kind of cool form to do, to say, hey, this is the volume just of the cut. In other words, all you have to know is the cut. I didn't even know that before. When I first stared at it, I thought, I don't even know how to set this up, how to get started. I don't even know what I'm doing. But now I realize the volume is entirely based on one choice that you make. You didn't have to make 2 choices, just one. Choose C, and then everything else happened. You got numbers for everything. So this is nothing more than what I just did a second ago, except for the language of algebra is doing with letters what you've already been doing with numbers. Since I did 3 tries at it, I realize now, oh, okay, that's not so hard. Now, I have to take the derivative of this, and this is like product rule, except for there's 3 things, and I don't really like that. So I'm going to mess with this some. Like, for instance, I could multiply this out, like 32 times 18. What is 32 times 18? That's 576. So I have 576, and then I have 32 times minus 2, which is minus 64, and then another minus 36. So minus 64 minus 36, that's negative 100. That's nice. So that's negative 100c, and then finally 2c times 2c, negative times negative, is positive 4c squared. But then all of those are multiplied by this c up here, so that means this would get a c, and this would be a c squared, and that last one would be a c cubed. So those are the same equation, but don't you think the second one is a much easier derivative to take? We don't like multiplication signs because that means product rule, and we certainly don't want 3 things, 2 multiplication signs, because then it's a really confusing looking product rule. Well, hey, this is just good old power rule, you should say, and so this is easy. So that was actually worth doing, I would say. So what is the derivative of that? 576 minus the 2 comes down to the 100, and then the 3 comes down to the 4. Isn't that the derivative? And we said earlier in this chapter that I can find maximums by taking the derivative and setting equal to 0. So that's kind of cool. Before we do that, let's just take a look at something in Desmos though real quick. Actually, let's not even look at the graph just yet. So just to check to see if this is actually working, like I went in there and I said v of x equals, and I wrote down the equation that we had was 32 and 18, right? Yeah. Then notice I just let myself make a guess for C, and then I said, what is the volume of C? In other words, a second ago we said one of our cuts was 2, right? And wasn't that our volume, 784? And then we tried 5, and wasn't that our volume, 880? And then we tried 7, and wasn't our volume 504? Was it 504? I don't remember that one. Hopefully it was. But notice now I can do something, and again, I still don't need calculus, and that's the thing I just want to illustrate here. Does it make sense that you could just slide this around? And what I want you to do is just watch the volume. It's 504 right now, but let's just guess our way. And this is what's cool about the technology in the world that you live in. You don't have to just keep guessing and guessing and guessing. We could actually just drag this around now. So let's see, what's the biggest volume I can get? Notice it's going down, down, down. But if I go this direction, 700, remember 784 was my biggest one. See how we got 792? No, it was 880, wasn't it? 880 was our biggest. Notice how it went over 900, 939, 945, 960, 62, 64. Oops, it just went down. So it's like right in there somewhere, like 3.7. So right in there somewhere is the biggest one. And now let's kind of play a little, just kind of play a little more. So that's 964.8. If I went down to 6, 964.2, that's smaller. So remember 7 was 964.8. But if we went up to 8, that's 964.2. So would you agree that we guessed and checked, except for in a little more algebraically sophisticated way, thanks to Desmos, and the best answer is 3.7. Now, is it 3.7 or is it 3.71 or 3.72? Well, I don't know. Let's try. So let's stick a 2 in there. So that's 6479. 6480, that got bigger. 648.0 got bigger. 6481, that's bigger still. So maybe it's actually 69. That's also 80, 6480. So it's actually like 3.695 or something. I don't know. But we're darn close now. Close enough, right? Like if you're actually going to build this box, you don't care to be this accurate. So of course, if I do turn the graph on, it's a cubed graph. And what we're actually looking for then is this point up here, which again, it's kind of cool that Desmos kind of knows that's one of the points that's interesting. So I didn't even have to, use the graphing calculator. I just clicked on that point and said, oh, you want to know that point? And notice I was honing in on it, but I wasn't actually right. It's really 3.703. And by the way, that's just rounded off. It's actually further than that. So 3.7 was a really close answer. So I'm looking for that point. But again, you know, as soon as you wrote the equation, you can find maximums by taking the derivative and setting it equal to 0. That's a much more sophisticated way. But again, I want to say, do you really need calculus in the world that we live in? The answer is not really. I mean, these are practical in some respect, but I can get this by guessing and checking. I didn't need to even have Desmos. I could have just kept guessing with my calculator. But that's the point of algebra, is like, why guess when you don't have to? And ultimately, calculus allows you to get this without even drawing the picture. So without calculus, we have the answer, but let's go finish the calculus. So I took the derivative. I need to set that thing equal to 0 because, as you know from the previous graph, that max up there happens where the slope would be 0. So that's kind of a cool trick to find it. And and I think I'll write it out. I don't usually just stick this in my calculator, but quadratic formula says C would be equal to negative B, which is 200, plus or minus the square root of, I'm going to figure this out real quick. So b squared minus 4ac. So 200 squared minus 4 times 12 times 576, which works out to 12,352. All divided by 2 times a. So that's the exact answer to this. Well, there's actually two answers. And maybe you remember from the graph would say there's two answers, because isn't there one up here at the top? But isn't there also one down there at the bottom? But why is the one on the bottom not realistic? What about it?
Because that's for the minimum volume you can get with the box of that shape.
Yeah.
Yeah, and it comes out negative, which is even worse. What were you going to say, Felix?
Oh, never mind.
Wouldn't your piece of paper just kind of like, it's kind of unreasonable to do that because we're working with a geometric shape with a paper that has only it has limits.
Yeah, the paper has limits, and you're actually going into a world that isn't even real. Realistically, as we said a second ago, the cut has to be, since our smallest measurement was 18 centimeters, you can't, if you make a cut of 9, you don't have a box anymore. So realistically, the only part of this graph that makes any sense here is kind of that part right there. So even though there's two algebraic answers to this question, the larger one doesn't make sense in this case, because you can only make a 0 to a 9-inch cut or 9 centimeter cut in this particular problem. And so it's just interesting that, you know, only part of this is actually real for us. So just so that we have it in front of us, I'm gonna stick that up there. We have our guess, and I'll put this in the notes that way. So we know it's 3.703. But of course, because this is a real problem, you would not want to answer it exactly. You'd want an approximate answer. So I get two answers for this. One of them is 12.96, and that's what I'm saying a second ago. That doesn't make any sense. Or C could be 3. And I'm going to write this whole thing down, 7025187. You now know that this is coming from a square root. So mathematicians call those irrational numbers, which means that decimal actually goes on forever. So in a sense, this problem is actually impossible. And ancient mathematicians argued about this a lot. I wish I could go into that, but it's really fascinating because when you write the square root of 12,352, you sort of feel like, oh, I just did something. But remember, you can't, that doesn't do any good until you actually take the square root. And when you do, you get a decimal that goes on forever, which you have to round off. In a practical sense, then round it off, who cares? But in a theoretical sense, it's impossible. I don't know if it makes any sense to you, but the number goes on forever.
So on a test, do you want us to like cancel out a number that doesn't make sense? Or do you want us to like put a note by it that says this doesn't work or something?
Yeah, I mean, my problem will just be something like, you know, find the size cut that would maximize the volume of this box, and I would want the answer to be 3.7 centimeters. And the other one, although it might be part of the math, isn't part of your final answer. You don't have to cross it out. You don't have to say it doesn't make sense, but just don't say both. Don't say either one of those would work, because they don't. You don't even have a box if you make a 12.96 centimeter cut. So the max is at a cut of approximately, and I don't care how you round. But obviously this is a calculus class, so I'd want to see the derivative being taken, because this is a calculus class. But as of illustrated, you don't actually, because of graphing calculators, you don't have to do that to get this answer. But check it, you know, make sure it works. Go back to the graph, and this is what I'm going to add in right now. What I'd love to see on a test, as I often say, is if you did screw this up, that you would have the graph, and then you'd steal the answer from the graph, which, like in this case, tells us the answer is clearly 3.7. So to say the answer is clearly 3.7, but I don't know what I'm doing. I'm terrible at calculus. I'm terrible at algebra, whatever. And I mean, that's actually kind of cool that you can still get it, even though you're getting it wrong relative to calculus. So it's kind of like, check. Again, I was gratified in the last test to see how many people said verified with Desmos. You know, it's kind of cool. But you see what I'm getting at? Like writing the equation for yourself, it's no joke. Like that's hard. Most people can't just stare at this and do this, but you might surprise yourself if you're not afraid to just weigh in and start writing stuff down. Like you might actually be able to do this when maybe maybe you thought you couldn't. So let's try another question. Another example.
So aren't inflection points involved at all in that equation? Like on a test, would you ask for the inflection point at which the volume is no longer, like now the volume is going up, but now the volume is going down?
That's a good question. Because yeah, what the inflection points tells us is like, if you start with no cut at all, if you have no cut, then you have no box, it's still laying flat. But notice, if you start making cuts in it, the volume just starts rocketing up. But it's beginning to slow down up here. Does that make sense? The second derivative here would be a really big number because it's saying the volume is increasing really quickly because it just went from 0 to something and it's increasing really quickly. But it's beginning to level off. The second derivative is now smaller and smaller and smaller. And finally, when you reach this peak up here, and so yeah, the inflection point tells you about how quickly the volume is actually changing, but you don't need it for an optimization problem. You wouldn't need it. It's a good question.
So I was thinking you could theoretically just keep taking derivatives over and over until eventually you'd get like just a constant number, right? Does that sort of like imply that like all like equations can kind of just be reduced to like sort of one number that kind of defines its behavior? Or
there is something to that. And do you understand what Felix is saying? He's saying if you took the derivative of x to the fourth, it'd be 4x to the third. And then the derivative of 4x to the third would be 12x squared, and the derivative of 12x squared would be 24x, and then finally it'd be 24. In other words, eventually the derivative becomes a constant. But keep in mind, you got to think about what the meaning of that is, because a derivative is a change. So by the time you get to the fourth derivative, you're talking about the change of the change of the change of the change, and it starts to be like, what does that mean? But you're right in the sense that it reduces. But remember, that's not true for sine, because the derivative of sine is cosine, and the derivative of cosine is negative sine, and the derivative of sine is cosine. Like it never turns into a constant. So it does in the case of the cubed equation.
well, yeah, I mean, we ignore like a veil in the chat, for example, but like for the nice ones, like it does kind of turn into a number, and I was wondering if there's anything to that.
As a matter of fact, that turns into be a major thing, because in Calc 3 spring term, if you're still with me, we're going to talk about how cubed equations can model sine waves and stuff, and how you can actually make a parabola or a polynomial equation model anything, and it's kind of based on exactly the principle you're talking about. So yeah, that is actually a thing. But just keep in mind, derivatives stop having a really much of a meaning once you get to the third derivative, because now you're saying it's the change of the change of the change, and then it's kind of like, what does that actually tell me about the problem? It starts to get tougher to visualize, I guess. All right, future math teachers, let's make our own problem up right now. So let's see, I want a rectangle under a parabola. We're going to try to maximize that area of that rectangle, but let's see, let's make our own parabola. So you're a future teacher, you got to be able to make stuff like this up. So let's say I want the parabola to hit here and out here, and we'll say that's at 0, and maybe this is out at 18, and I want the parabola to kind of go like this, and then what we're going to talk about then, is like what size rectangle would be the biggest. Would I go here? And I need a different color. Would I go here and have it be a nice wide rectangle? But unfortunately, being wide makes it really short. Or would it be, no, it should be a lot taller. I want it to be a nice tall rectangle, but then of course that makes it really narrow. And so, which one of those, if the rectangle has to live stuck under the parabola, if you will, like where's the biggest area? And so you future math teachers, and the problem on the assignment, you're just going to be given the equation for this. It would just be, y equals something x squared. But, could you make one up? Can you make this up yourself? Like how would I make a parabola up that would look like that? I want it to hit at 0 and at 18.
Well, we know that y is 0 at the points 0 and 18. So
yeah, so y is 0 at those 2 points, and we did look at this in one of our projects, you may remember. I kind of forgot what that was about, but I remember.
the chair project.
The chair. Yeah, we wanted our chair to hit a certain location, and so if it's going to hit at 18 and at 0, it would have to be, this would have to be x minus 0, and this would have to be x minus 18. So that would be my parabola, x times x minus 18. But which works out to be x squared minus 18x, but that's not quite right yet. Does anybody know why? Again, I'm just you future math teachers. Why is that not quite what the pink parabola is going to look like?
Aren't we missing our constant?
If we add a constant to this, it's going to move the graph up. And if the graph moves up, it won't hit at 18 and 0. So it's missing a constant, but in a sense, I want it to be. So because it hits at 0, that's why it's missing a constant. If it was at 1 and at 18, it would have had a constant in it. But basically, it's because I chose 0.
Do we need to put something in front of the x, like, I don't know, 2x squared minus 18x?
Yeah, you may remember from the project that you can multiply by something. And in this case, you have to, because don't parabolas with a positive 1x squared, don't they face up? And this is upside down. So I want it to face upside down. So remember, you can multiply by something here. In this case, because I want it to be upside down, and multiply it by -1. And so 18x minus x squared would look like that as an example. Again, I just show you that for future math teachers. You don't need to be able to make this for yourself, but that's an example of like what it means to think and really understand things. This is the problem. This is what the problem would be on a test or on an assignment. Find the maximum rectangle that would fit underneath that pink parabola, and there's its equation. So again, you should find yourself thinking, I have no idea how to start this. I'm just going to stare at it. And you've done that before. When you stare at things, nothing changes. You just stare and stare and stare. Occasionally you have like, aha, I got it. But all I'm saying is don't be afraid to guess, like just play around a little bit. So that's what I'm going to do now. I'm going to illustrate the same thing I did before. Like, let's say I went in, I don't know, 2. I went in 2. So there's where that rectangle is located. It's located at x is 2. Well, since I'm trying to find the, maximize the area, the area is length times width, or length times height. I guess I'll say height in this case, since it's vertical.
Wait, wouldn't it be important to know where the top of the parabola is? So we know
Maybe, but
how
my
tall our
orange,
box can
my
be.
orange rectangle isn't hitting it. And by the way, according to what you were seeing, if I made it negative, it flipped it upside down, but it doesn't have to be -1. It could be -2 or -3, which would make it really tall and skinny. So I just chose -1 just to make it go upside down. But the problem is, like, how does that help me? Do I know either the length or the height because of that location? Or maybe it's the other.
I was more thinking for your green box, like how tall can your green box go under the
Right.
parabola?
Yeah, in other words, a maximum. What you're really getting at is kind of domain and range. Like last time we said, it turned out you couldn't make a cut bigger than 9. If you made your cut 9, you don't have a box, so your cut has to be less than 9. And the same thing might be true here. Like I can only choose certain values for this. But in a sense, and again, I think you could stare at this a while. Or maybe do this the other way. Like you say, I'm going to make this distance, I don't know, 14. Like that's 14. That's how long I'm going to make it. Does it make sense if you choose that to be 14, since the overall distance, the rectangle is sitting on top of the x-axis? Does it make sense, since the overall is 18, that this distance is 2 and that distance is 2? I don't know if I need to know that, but. So that makes a total of 18. So in a sense, I'm just guessing. That's all I'm saying. I'm just guessing with this because I don't really know what to do. That's what this should feel like to you. So I say, okay, then my length is 14. I chose 14. That was kind of my guess. But how am I going to get my height? Well, obviously it goes up and hits the parabola, but what good does that do me?
Do you need to find the y value for that point
Yeah.
on the line?
That's exactly right, Cheyenne. Isn't that y coordinate right there? Can't that be found using this equation? What do I plug in to get that?
Your x coordinate.
Yeah, your x, which isn't 14, it's 2. So if I plug 2 into that equation, isn't it giving me the y coordinate of the parabola, which would be the height in this case? So let's see, that'd be 36 minus 4, which is 32. So there, by guessing 14 or 2, I don't really care which one your original guess was. I'll say it was 14. Since it was 14 or 2, then I can say the area of that rectangle is length, which is 14 times 32, whatever that is, 14 times 32. It's 448. Again, that'd be square inches or square centimeters or whatever. So I have one answer to this. There's my first guess. But now let's go back and we'll try something else. Maybe this time I chose, this distance all the way across to here. Maybe I'll choose that to be 7. So in a sense, my guess is 7. So since the parabola is symmetrical, and by the way, this would not work for a cubed equation because it'd be more complicated for a cubed equation because you could not assume both of those sides are symmetrical to each other. So if that's 7 and 7, that's 14. The whole thing was 18, then that means this is 4. So my width now is only 4. Well, that's not a very wide rectangle, but it's going to get really tall. So this time my length is 4. And my height would be equal to y of 7. Stick 7 in for x and you get, so that'd be whatever 18 times 7 is, minus 7 squared is 49, 77. So my area is equal to 4 times 77. And again, you might think, I'm going to get the same answer. I'm going to get 448 again, but you don't. You get 308. So guess as many times as you need to feel like I see what's happening now. I know what I'm doing. I'm getting faster at it. As soon as you're fast enough, then you can just start doing math to it. So now let's actually find the equation. Let's see, we haven't done red yet. So let's actually find an equation. We can now do that. For a, I'll say a is a function of x. And why am I saying x? Well, it's because I'm going to go back to this drawing up here. And this time, though, just draw this in as a different size. This red one right here. I'm going to say that red guess right there is x. So that's what I'm going to make my guess to be. I could have made it the width of it. I could have made it that. I can make it anything I want, but I'm just saying that's going to be my x. And I'm saying that because that's what I have to plug into this equation over here anyway. So I might as well just let that be what it is. So let's see, what did I do then a second ago when my guess was back here, when my guess was 7, if you will, my guess was 7. I had to add 7 and 7 together and take it away from 18 to get 4. Isn't that what I had to do to get this? So my length then is equal to 18 minus 2 of those guesses, 2 of those x's. I think I can see that now. And then I got my height by just plugging 7 into the equation. Well, in this case, my height is just x is plugged into the equation. So since the equation was 18 minus 18x minus x squared. So now I actually have expressions for both of those statements. I have equations for both of those statements. And so don't know about you, but I just find myself, I don't think I can do this. I don't think I can just write this equation down. I don't think I can just write down an equation for a as a function of x unless I've done a little bit of guessing and checking. And so that's my equation now. So there's the area of that rectangle for any x you might pick. And again, I chose this time for my x to be kind of the x coordinate. So I called it x. It's like, how far over do you want to go? So now I say, well, great. Now that I have this, as far as like video you might see, or maybe there's some help in your book or whatever, it's probably going to reduce this to steps, but it's going to probably say something like step 1, write an equation. And well, we just did that, but that's hard. That is not step 1. It's like step 7 after you've guessed 6 times and you realize, oh, okay, now I know what's going on. And of course, to find the maximum, in this case, I'm trying to optimize, make the biggest rectangle fit in there I possibly can. That's why I want to take the derivative of that and set it equal to 0. But again, I'm looking at this just like before and saying, when I'm staring at that right now, I'm thinking that doesn't look very easy to take the derivative of. It looks like power rule, or I'm sorry, product rule. So I'm thinking, I don't really want to do product rule. I'd rather multiply it out. So I'm going to keep going and multiply this out. So 18 times 18x is 324x. And 18 times x squared is 18 times x squared, and 2x times 18x is minus 36x squared. And finally, minus 2x times minus x squared is actually plus 2x cubed. And so I see I have 2x squared terms, so that's a total of minus 54x squared. So that's what I want to take the derivative of. Please interrupt immediately when you have questions. So the derivative of 324x is 324. The derivative of 54x squared is minus 108x. 3 comes down multiplied by the 2. So there's my derivative equation. And again, it's like, hey, you're going to get 2 different answers to this. That seems weird. But remember, based on this graph, just to stare at this ahead of time, does it make sense? X, based on this picture, X has to be less than 9. Because if I make X go right to the center, then I just have a line there and there's no rectangle. So X can't be bigger than 9. So probably one of these answers is not going to be between 0 and 9. It might have to be between 0 and 9. So this time I'm just going to stick this in the quadratic formula. But as I've said before, make sure on a test you actually at least say quadratic formula and then, just tell me the answers. But in this case, again, notice it's backwards. A is not 324, A is 6, and B is negative 108, and C is 324. I got X is approximately 3.8038, and it goes forever. And I got X is approximately 14.2. Oh yeah, it can't be that one. So there, I found the max. The max happens at 3.8. Now, when I go back and look at my guesses, maybe that helps me. Maybe that tells me something. Let's see, when I guessed 2, I got 448. When I guessed 7, I got 308. I only had 2 guesses. So, and keep in mind, there may be 2, read the question carefully, because notice what I really just found is nothing. Like, what if the problem said find the length and the width and the area of the rectangle? Does it make sense 3.8 is not the width or the length or the area of the rectangle? It's none of the above. Like, X was that distance. So just because I want to kind of finish the problem, or at least make sure I understand what I just did, I'm really saying it's that distance right there that's roughly 3.8. So since the whole distance was 18 all the way across, if I go 18 minus 2 3.8s, it's really 10.4. So this is 10.4. And if I put 3.8 into the equation, 18 times 3.8 minus 3.8 squared. I'm actually getting a height of 53. .96. So, you know, just pay attention to the way the question's worded. Even though I did all the hard math, it might ask what's the area of the largest rectangle. Well, now I got to multiply 10.4 times 53.96, which is 561.2 approximately. And again, that'd be square centimeters, square inches, whatever. But the idea is just to notice, hey, look, that really is bigger than the other two. I got 448 and 308, and this one's quite a bit bigger than that. So I did really find the biggest one. That's kind of cool. I never graphed this accurately. I never cheated on Desmos, but does it make sense if I went in and tried 3.7? Actually, maybe I'll do this really quick just because it might be worth your thinking. I'll say check. Find the area as a function of 3.7. Remember, I have this equation, either of these two red equations to look at. All I have to do is throw 3.7 in there to see what my area is. So I'm going to just type the parentheses version. So I'm going to say parenthesis 18 minus 2 times 3.7, close parenthesis, open parenthesis, 18 times 3.7 minus 3.7 squared. When I did that, I got 560.8. Notice smaller. What if I went on the other side of 3.8 and went up to 3.9, a little bit bigger? If I go second entry on my calculator, I can just go change all the 0.7s to 0.9s, and then this won't take me very long. When I did that, I got 560.9 as well, or actually a little bit different, 560.9. So notice that's kind of I now know for sure that really is the right answer because it's bigger. I went on both sides of it and I can tell, oh, look, it's going down. It's getting smaller. So clearly I must have got it right. That's kind of cool. But notice this took a totally different logic than the previous question. And again, I'd say this is far from practical. Like who would ever need to find the biggest rectangle that would fit under a parabola? Like this is playful. That's all this is. This is a mental exercise, if you will. Maybe the first question wasn't, but that one certainly was. But these are kind of hard. As I said, maybe there's one person in class too who could just quickly see an equation like this, but most of us are going to have to play around with this a little bit. So let's try one more. We have time for one more. All I can really do with this is just, you know, talk and give you examples and let you think about it. But let's try yet one third example, and let's try to maximize a cylinder inside a cone. This is kind of a cool problem. Maximize a cylinder inside of a cone. What in the world is that talking about? Well, here's the cone. And let's give this cone a certain dimension. Let's say it has a height of 20 centimeters, and let's give it a radius of 12 centimeters. That looks reasonable. So can you visualize the cylinder sitting inside there? For instance, let me make a copy of this because I'm just going to draw a couple of them in there. Maybe you say my cylinder is actually going to be nice and big. Well, big in what sense? Well, let's say it's kind of large in its radius. But of course it's so large it hits the side of the cone a little bit sooner, if you will. So is it that size, or maybe you think, no, I want it to be nice and tall. I want it to be nice and tall, but then unfortunately notice it isn't very wide. So
Just out of curiosity, since we're looking for which one has a greater volume, can you predict, like, is there any way you could predict which one has the bigger volume without doing any sort of calculus or algebra?
well, you have to do calculus. Like in this case, I'm giving you a certain cone. I'm telling you it's 20 and 12. But could you come up with a formula that took the 20 and 12 and just told you, almost like, don't let 20 be a constant? Can you come up with a formula that has H and R in it ultimately? I mean, that's a good example of kind of an extra credit problem. If you found yourself interested in one of these geometric type questions, is there some relationship between 12 and 20 that would allow you just to go, boom, the size is this? Or the radius of this blue cylinder needs to be, you take 20 and subtract 12 and you get 8 and you divide that by 2, it's 4. It's 4. And you just already know. It'd be calculus that told you that. So you can't get away from calculus, but you can solve all problems. We're trying to solve one right now. I want to give you a second to think about it, but what you should think is, what your first thought should be, yeah, the last two problems you did are no help at all. Like, this is a totally different question. Correct. This is no help at all. And I don't know what equation to write. Well, I do know the volume of a cylinder. The volume of a cylinder is pi times the radius squared times h. But it's like, how am I supposed to, I can't take the derivative of that. It's got r's and h's in it. And how would I do this? But again, what I have shown you in two previous problems is take a guess. Like, I drew two different cylinders, like stick some numbers in both of those. Choose a guess. Now, I didn't even tell you what guess you should choose. Should you choose the height first, or should you choose the radius first of that cylinder? I don't know. But you might be surprised by how much progress you can make if you're not afraid to just try something. I'm going to give you a minute or so before I proceed. All right, I'm going to launch in so we don't run out of time. I wish I could give you more time. But as an example, just to get you started, let's see. I'm just going to try to do this kind of proportionate to the picture. If the radius of the green cone is 12, then maybe I'll make that distance 8. There's my guess. So great. Radius is 8. So I can find the volume. Well, I can't. I need H. How am I going to get H? That's the hard part here. How do I know where that thing's going to hit?
So don't we kind of need to do some, like, I guess regular old like triangle math here, because we do kind of have like a little bit of a triangle for that height between, you know, the angle of the cone and the like 4 or whatever that we have for a side there.
That's right. One approach to this, and again, this is something that comes from speaking the language of math and algebra well, because this is not easy. But one option is to stare at this and say, I see some similar triangles. I see some proportions. In other words, in the large triangle, since the radius is 12 and the height is 20, wouldn't that be the same triangle as the kind of, or proportionate to this triangle over here? I think that's what Felix is getting at. That's one way to do this for sure. And isn't that and the main thing is you're trying to get the height involved somewhere. So if that's true, then those two triangles would be proportionate. I notice in this, since I chose my guess to be 8 and the radius of the green cone is 12, then 12 minus 8 is 4. That leaves this distance down here to be 4. So you could say 12 is to 20. 12 is to 20 as H is to 4. Or I could say 20 is to 12 as H is to 4. Maybe that'd be easier. 20 is to 12 as H is to 4. So a proportion. We'll do it. So that means H is 80 over 12. Maybe that's a nice decimal. Maybe it's not. I don't know. I don't think it's going to be 6 2/3. So as a result of my guess for 8, I did not have to guess height. And if I did guess height, that'd be wrong because it's got to hit the cone. I mean, I want it to be as far up in the cone as it can possibly get. So pi times 8 squared times 80 divided by 12 is approximately 1340.4.
What if you were to take the triangle of the inside of the cylinder instead?
What do you mean?
Yeah, make a right triangle with the 8 and the height of the cylinder proportional to the whole cone.
Yeah. There's other ways you could do this. I'll probably erase this just so it doesn't get confusing, but isn't there a cylinder there too?
No, I mean inside the cylinder itself.
Yeah. So there's actually 3 ways. That would be a similar triangle that I just described, and you're saying more like, are you saying from here? Something like that?
Yes.
Mm-hmm. Let's see, is that automatically, I'm not sure that's automatically similar to the other ones.
So
Think about that.
the way I went about this is we have 2 radiuses, right? We have radius 1, which is the radius of the cone, and radius 2, which is the radius of the cylinder.
Mm-hmm.
And radius 2 equals 12 minus x, right?
Mhm.
And then I took that and put that in the context of solving for the height of our cylinder. So using, oh, heck. Oh, so I made it, yeah, the right triangle thing. And then the length of the bottom is also 12 minus x.
Mhm.
And then you can substitute a bunch, and then you can plug it all into the cylinder equation, because we don't actually care about the cone's volume. We only want
Right.
the cylinder.
That's right. So the one thing I would say is, like, I showed you a way, but there's lots of ways, but I just got H as 80 over 12. So if you try a different way and you get 80 over 12, then your way worked too. I'll erase this, but just because, again, I think it'll get confusing, but could you even do this? Could you say, like the previous problem, I'm going to think of this as an XY axis, and I'll just find the equation of that line over there. Because aren't we doing this is kind of like the same thing. It was like a rectangle that was inside of a parabola, except I gave you the equation of the parabola. Could you go to this and say, well, I see that this hits up here, since the height of the cone was 20, it hits up there at 20. And since that's 20 and this is 12, that's a rise of 20 and a run of 12. So that'd be, since it's going left, it'd be, wouldn't that be its equation? So you could even make an equation out of that line. There's all kinds of things that you could do here. And again, that's good, but it's also bad, because I'm showing you the proportion thing is probably the easiest. But I'm saying, if you come up with a way to get 80 over 12, then good for you. Whatever works.
Doesn't that make finding our derivative harder because we have to do these proportion stuff?
Yeah, and this is all about the fact that what I really need up here is I need an equation with just V and one other letter. That's what it comes down to. I can't have R's and H's over there. That's the issue.
So would you build your H equation off of your R then? Because like your relation proportional, and then you could build your equation and then take the derivative.
That's right. In the end, you've got to have an equation that's V is a function of H, or V is a function of R, or V is a function of G for gas. It doesn't have to matter what the letter is. Let's do quickly one more guess, and maybe then we'll see a pattern and we're able to write the equation. So you'll notice I'll be able to go a little faster this time. So this time I'm going to say the radius of my cone is 2. So I've just chosen 2 as my guess. That's my guess. And then what did we do last time to get our H? Well, last time we said 20 is to 12 as the height here is to this distance there. And that distance, since the radius is 2 for the cylinder, but the radius is 12 for the cone, it's 12 minus 2. So it's 10. So if I multiply 10 times 20, I get 200. So H is 200 over 12. So if I take pi times 2 squared times 200 divided by 12, I only got a volume of 209.4. Which is way less. I mean, that was 1300. So that was terrible. That was a terrible choice that I made, a terrible guess, if you will. But the question is, now could we actually just write an equation for this? Could we just not guess? And what I'm going to try to do is find an equation v as a function just of r, since that's what my guess was. My guess was r. That's been my guess so far. That's the guess I chose to make first. Well, what we saw right here illustrates what I have to do to get h. So the h part of this was 12 is to 20 as h is to 12 minus whatever our guess was, whatever our radius was.
Couldn't you put it so it was like 20 times, like 20 parentheses 12 minus r over 12 times r, 12r?
Yeah, but not 12r, because if I solve this for h by multiplying 20 times 12 minus r, then there's just a 12 on the bottom, like that's my h. Not sure if I'm answering your question correctly, but
That's what I meant. I think I just said it wrong.
yeah, I think so. I think you're on the right track. So basically now I can say, here's my function, here's my equation. I can say v is no longer pi times radius squared times height, because now I can replace height with what we just figured out height was equal to, which is 20 times 12 minus r over 12. And so that equation only has, well, one unknown. That only has one unknown in it. And so now I've succeeded in the hardest part of these problems, and you should agree with me probably that that's hard. And so now I just need to take the derivative of that and set it equal to 0. And I won't be guessing anymore. I'll be getting the best volume I could possibly get. And notice 8 was a pretty good answer, but 2 was a terrible answer. So let's see, let's multiply this out. Well, what do I get? I don't want to take the derivative now because it looks like there's fractions everywhere. There's product rule, but I can see there's a pi divided by 12, and then there's an r squared, and then if I multiplied 20 into that 12, that'd be 240 minus 20r, and so then I could keep distributing r squared, and I'd have pi over 12 outside, and that'd be multiplied by 240 times r squared, which is 240r squared, and then 20r times r squared would be 20r cubed. And so for the first time, it's like, wow, that's weird. The volume as a function of the radius only is actually a cubed equation again. That's kind of surprising. So that equation looks like an easier derivative to take. You're more than welcome to distribute pi over 12 into that mess too. Perhaps you think that makes more sense. You might not be wrong about that. I could simplify that too. 240 over 12 is actually just 20. But 20 pi over 12 doesn't simplify quite so nicely. Maybe you think it looks better like that. Well, now you're in a position to take its derivative and set it equal to 0. So the 2 comes down front, so now that'd be 480 pi divided by 12r. And the 3 comes down front, so that'd be 60 pi divided by 12r squared. And we get kind of lucky here because 480 divided by 12 is 440. And 60 divided by 12 is 5, so that'd be minus 5 pi r squared. And of course, what I'm after is, when is this thing equal to 0? Notice this doesn't have a constant term. It just has an r and an r. So I guess I could take an r out, and that would leave 40 pi minus 5 pi r. So r equals 0 is an answer. But of course, what that is a minimum. That's a minimum volume. Because remember, minimums and maximums are the same as far as slope is concerned. Slope equals 0 gives you a minimum or a maximum. If you have no radius on your blue cone, back here, if you have no radius, then you have no volume. Like that's the smallest volume you could possibly get. You have none, thanks to the choice of a radius being 0. We were looking for actually a max though, so we don't kind of want that one. So the other one, when 40 pi minus 5r equals 0 would mean 40 pi equals 5 pi times r. So if I divide that away, I get r is 8. Again, we got lucky. It was exactly 8. How else did we get lucky? My first guess up there was actually the right answer. That seldom happens. But that 1340 was apparently the biggest volume, and I just sort of guessed it right off the bat. That was kind of lucky. And so one of you, I can't remember if it was Felix or Eve, said something about, you know, is there some pattern to that? Could we have known that was 8 somehow just by looking at the 12 and the 20? My first conjecture is maybe it's just 12 minus 20. That'd be nice if it was that simple, but I have a feeling it isn't. I got to let you go, so I'm kind of going quick here. So the max volume of the cylinder happens when r is equal to 8. Again, the problem might go on and say, good, you found the radius, but you know, what's the height and what's the volume? Like they might want you to list all that stuff. But since we're out of time, I'll just stop where the hard part of this is done. How's your brain? Is it hurting? The only thing these 3 problems had in common is to illustrate that it's very hard to write your own equation and that you're going to have no success at this unless you're willing to play around with it a little bit. Keep in mind that as a teacher, I could have you do great on this test by just giving you, say, 2 or 3 examples, and we just practice those examples a whole bunch of times until you kind of have it memorized, like you didn't make it for yourself or deeply understand it. But then I just give you a test question and assignment questions that are like that, and all you're doing is practicing a process. And I'm sympathetic to that because I want people to be able to pass this class and get on with their life, which probably will not involve you ever needing to use this. But if you ever do need to use this, it won't be because you're trying to fit a cylinder inside of a cone. Does that make sense? It's more going to be because you're trying to maximize the profits at a company. And so you're like, should I buy this really expensive machine, which will save labor, but then the machine costs more money. And then I have more money in machine, but less labor. And or should I buy a cheaper machine so it's less cost there, but then it's more labor? I mean, that's realistic. That's why business calculus is a thing. You want to maximize your profits. So, you know, will you be able to think? That's where you're actually going to use this, and it might not even involve writing complex equations like this. I'm giving you kind of geometric examples, if you will, to think it through, and that's kind of fun from a theoretical sense. But I wouldn't call these problems very practical. Mathematicians will act like they're practical, but you know, can you imagine anybody doing any of these things? Well, maybe the box one at the outset. Maybe you could kind of imagine somebody doing that one. But you're never going to see anybody but a pure mathematician do the next 2 questions that I asked. That doesn't make any sense at all. So my advice would be, you have lots of time before this assignment is due to stay after class and ask me questions. My advice would be wade into the questions tonight, because all I'm going to do tomorrow is just give you some more examples, and I'll look a little closer at the assignment and try to be a little more hintish toward the assignment. But I just want to give you time to kind of soak on this a little bit. There's nothing else I can teach you about this, but I just think we need some practice. And if I can do some examples that are more like the book assignment, that'd be helpful. All right. You stay after if you like.
You got a second to chat then?
Absolutely.